This is video number 16 for artificial intelligence, and I am just going to finish off talking about planning. And the final subject we have to look at here is clearly closely related to the last video. In the last video I talked about taking a planning problem and encoding it so that it could be addressed by a SAT solver. Now I want to look at a general method for representing planning problems in such a way that they can then be re-encoded as constraint satisfaction problems. And the overall idea here is very similar to what we talked about in the last video. You take the planning problem, re-encode it as a CSP, run a CSP solver, and extract a solution to the planning problem from the solution you get from the CSP. So to start with, let me just give a very quick review of what you need in order to set up a CSP. You will have a number of variables, each will have a domain specifying what values it can take, and then you have a set of constraints, and each constraint involves a set of variables and tells you which combinations of values you can assign those variables to. And then a state is an assignment of values to some or all of the variables, and an assignment is consistent if it doesn't violate any constraints and complete if it assigns something to every variable. And we're looking for a consistent and complete assignment as a solution to the problem. So the first thing I want to do is set up something called the state variable representation. And for the time being, we're essentially moving away from CSPs, because what I'm going to do here is set up yet another particular language in which we can represent planning problems. This is different from strips, because strips was aimed at partial order planners, and this is aimed specifically at allowing you to express plans in a format that is amenable to being transformed into a constraint satisfaction problem. Okay, so the state variable representation is the name for this particular way of representing planning problems. Now, in order to set this up properly, I need to talk about domains. And from the outset, I'm going to direct your attention to the note at the end of this slide, because we have to be careful not to confuse the domains that are used by the state variable representation, which I will always be denoting as a beautiful curly D, like this one, and the domains that are used for CSPs, which I will be denoting using a bog standard, ugly and boring capital D. But it's important that you don't get those mixed up. Initially, I'm only going to be talking about domains for the state variable representation, so the Ds will be curly. Later on, we need to make a distinction between these and the domains that are attached to the CSPs. Now, the domains that are associated with the state variable representation are just essentially used to organize objects. In fact, I suggest that the first time you look through this bunch of slides and try and think about this representation, you don't worry too much about what the domains are and what they mean. They're needed in order to be explicit about what you're defining, but it's almost certainly easier to understand the overall method without worrying too much about these at the outset. Essentially, all we're doing is associating domains with different groups of things that are of interest within our planning problem. In the running example, climbers, places, and objects. And those domains, or more specifically unions of them, are used as a basis for defining relations and functions within the state variable representation. And the example I give here is the relation of something being above something else. You might want to be able to say that the climber is above the rope, in which case the domains here have to involve unions of domain 1 and domain 3, on the slide. But the way to think about it is simply that above is a relation that refers to two things within the planning problem, and above AB means that A is above B. Now in that example, above doesn't change over time, so it's what's called a rigid relation. Now, clearly within our running example, that's not realistic, because whether or not one thing is above another can change over time. And so once again, we need to introduce some idea of the state of the world, and we need to allow anything that can change over time to depend on state as one of its parameters. Now, a function that allows us to specify location within the planning problem, and the function will take some object or other within the planning problem and a representation of the current state of the world, and it will give us back the location of its parameter, and that's a state variable. So in the example here, we may establish that the gorilla is at the joke shop in some given state of the world. So that's quite nice, and it actually immediately solves some of the problems that we saw with the idea of converting things to a SAT problem. Because if we're talking about something like location, a function may actually be a very suitable thing to use, because the location of something acts very much like a function. Everything has to be somewhere, and everything can only be in one place at a time. And seeing as functions are defined for all parameters, and they have a single value, that's a perfect way of setting this up. Now, the way that we build this up is going to look fairly familiar to you, because it has a lot in common with the Strips language. And in particular, in order to represent actions within the state variable representation, each action has a name and a set of preconditions and a set of effects. Now we set this up so that names have a list of variables that are involved in the action, and once again we have a collection of preconditions and a collection of effects. And the preconditions can include state variables or rigid relations, and the effects are just new assignments to state variables. So here we're saying that x buys y in location L. And the preconditions for this to be able to happen are that x is at L, that L sells y, and that L is actually the current owner of y. And the effect will be to modify the ownership of y so that the owner of y becomes x. Now this is entirely as basic and straightforward as it looks. All we're doing is saying that things that don't change are rigid and they don't depend on the state S. And that anything that does change is modelled using a function for which one of the parameters is S, allowing the value of that function to change according to the state. Preconditions can either be achieved or not, depending on whether the functions have the correct values at the time that you try to apply the action, and the effects of an action just change the way in which one or more of the functions maps its parameters to an output. Now, goals are entirely similar. A goal just involves getting some of the state variables to have the right values in some state. So our goal might be that the climber is at home, and the rope is owned by the climber, and the gorilla is on the spire. Now in what follows, I'm going to suppress writing S as an explicit parameter, because it just makes things cluttered. But it should be entirely clear from context whether or not something is a state variable or whether it's a rigid relation. Now the first thing I need to address here is how one actually represents a state. Well, that's easy, because a state just tells you an explicit definition of what every state variable does at the moment. So a particular state of the world may tell you that the joke shop has the gorilla, where we've now suppressed the argument s in the has function, because we're now assuming that that's implicit. And also that climber 2 has the first aid kit, climber 2 has the rope, climber 1 is at the joke shop, climber 2 is at the spire, and so on. A state is just a complete exhaustive definition of each of these state variables in the form of a function. And the way in which we can update states just involves changing one or more of those function values. For example, I could change this state by saying that the rope is no longer owned by climber 2, but it is now owned by climber 1. Now I have a different state, but everything that I need to know within the planning problem about the state is exhaustively defined. So, in general, for each state variable, we consider all the ground instances, okay, all the instances with the variables replaced by actual values, with arguments that are consistent with the rigid relations. I'm going to come on in a moment to exactly what that means, but basically it means you don't consider possibilities that the rigid relations won't allow. And then a state is just a collection that tells you for each ground instance of a state variable, in the example at the top of the slide, like has gorilla, has first aid kit, has rope, out climber, and so on, that ground instance v equals some specific value c. And we can define the initial state of our problem in precisely this way, because in the initial state we know that the joke shop has the gorilla, but the hardware store has the first aid kit, and the hardware store has the rope, and both of the climbers are at home. So the start state would look different, but again it's just an exhaustive enumeration of all the function values for all the relevant possibilities that they can take as their parameters. Now, given that we have a definition of state, we can now use it to determine whether or not, given a current state, any particular action can be applied to it. So here I have a state, and I want to apply the action that corresponds to climber 1 buying the gorilla in the joke shop. Now, if you look back a couple of slides, you will find that in the definition of buy XYL, if I plug in x equals climber, y equals gorilla, and l equals joke shop, that the three preconditions become has gorilla equals joke shop, and climber 1 equals joke shop, sells joke shop gorilla. And so I can actually apply that action in this state because all the preconditions are achieved. Now, because the rigid relation says that the joke shop sells gorillas, I'm allowed to use that combination for y and l. Notice that there's nothing that says that the joke shop sells fruit bats, and so we would not consider an action like buy climber 1 fruit bats joke shop because it is not consistent with the rigid relations. Sells is a rigid relation, it doesn't change over time, and we only consider things that are consistent with those. So that means that we can, if we wish, apply the buy action in this state. And I hope that you can now guess the way in which one updates a state in the light of having applied an action, the effect of that specific buy action is to change the ownership of the gorilla from the joke shop to the climber. And that simply corresponds to updating the definition of the has state variable so that for the parameter gorilla, its value is now climber 1, whereas it used to be joke shop. So formally, we can think in terms of this function gamma that takes a state and an action and gives us the next state And the new state just modifies the state variables that correspond to effects of our action and leaves everything else unchanged. So, we now have set up enough that we can represent states of the world, we can represent actions in terms of preconditions and effects, we can represent a start state, we can represent a goal, and the idea, as usual, is to come up with a sequence of actions in such a way that each is applicable, and in such a way that if we start from the initial state S0 and we apply this sequence of actions, then the states get updated in such a way that the final one contains each element of the goal state. And now we have another big search problem, because the idea is to search for a specific sequence of actions that will achieve this. So what we're going to do now is look at a procedure that one can use to take any planning problem that's been expressed in this representation, the state variable representation, and transform it into a constraint satisfaction problem that we can use to solve it. Now this has something in common with the idea of transforming to an equivalent SAT problem, because we're going to have to try increasing time limits for the possible length of the plan, and at each stage searching for a solution, and then if we can't find a solution, extending the potential length of the plan by another step. And the procedure works like this. Let's say we've chosen big T as the number of steps within which we think we can achieve a plan. The first step in transforming into a CSP is that for each possible time step in that range, the CSP has a variable called action T, and its domain contains all the ground instances of any action. So the idea here is that because these are variables, a solution to the CSP will assign each one to some possibility. Action T denotes the action that a successful plan should take at the Tth step, and the value it gets is the ground instance of an action in the state variable representation. So if I move back a little bit and just look again at our definition of the by action, what that means is that you can substitute x, y, and L in by in all possible ways. Each of those ways gives you a ground instance of the by action, something like by climber1 gorilla joke shop. And those ground actions are possible values that can be assigned to an action variable within the CSP. So for example, at some point in trying to solve the CSP for the running problem, we might find that action 5 is that we should attach the gorilla to the spire. And once again, I'm going to emphasize that you need to be careful to distinguish between domains for the CSP and domains for the state variable representation. Here, this is a domain for a variable, namely action T, and those are both part of the CSP problem. And the values that appear in the domain for this variable are ground instances of actions as specified in the state variable representation. And we also have this special one here, none, which means do nothing. Okay. Now, the second step is to encode ground state variables as CSP variables, and with a complete copy of all the state variables at each time step. Now what am I getting at here? Okay, let's just go back a little again. A state is defined by specifying an actual value for each ground instance of a state variable. So let's say the state on the left here is at time t, and the state on the right is at time t plus 1. What we're saying here is that within the state at time t, the one on the left, we're going to let has gorilla, has first aid kit, has rope, and so on correspond to variables within the CSP. And the domains for those variables contain all of the possible values that those state vectors can take. So has gorilla on the left at time t will be a variable in the CSP, and its domain will include joke shop and anything else that can be the value for has gorilla. On the right, at time t plus 1, the CSP will have another copy of all of those variables, one corresponding to has gorilla, one corresponding to has first aid kit, and so on. These are for time t plus 1, and they will have the same domains. So for example, at some point in searching the plan, we might try to find a solution that has location 9 of climber 1 equals hospital. We will originally have defined location as a state variable, and one of its arguments could be climber 1, and one of its variables can be hospital. Now we have a copy of location climber 1 for every possible step in the plan, and for each copy, the corresponding domain contains hospital and any other possible locations within the world that we're modeling. So now we have variables that can represent the state within the state variable representation at any given time in a plan, and we have variables that represent an action that should be taken at each time within a plan, and what remains is to link those together. Actions have preconditions and effects. So we now introduce constraints into the constraint satisfaction problem to enforce the fact that certain actions will be possible and certain actions won't, depending on the value of the state variables. And we can do that by taking each precondition, and each precondition looks like an assignment to a state variable, and we say that the action at a given time can only take on some specific value if at the same time a state variable that's one of its preconditions has a value that's compatible with it. So again, if we look at the action by xyl, and we know that it has the preconditions that x is at L and L sells Y and Y is at L, and we know that sells YL is only true for L is joke shop and Y is gorilla, so we only need to consider those values. Then we're going to introduce a collection of constraints that looks like this. We're going to say that at time t the action can be by climber 1 gorilla joke shop, provided at the same time climber 1 is at the joke shop. So we paired a ground action with the ground version of its first precondition. And we'll also introduce a constraint that says action t can be by climber 1 gorilla joke shop, provided that at the same time has gorilla is joke shop. So, in order to buy climber 1 gorilla joke shop, we have to have the preconditions at climber joke shop and has gorilla joke shop. Each of those preconditions is turned into a binary constraint within the CSP, and those are included for all possible times t within a plan. And we do that for all ground actions with their corresponding ground preconditions for all possible times. Now the final step is to encode the effects of actions. I hope you can see where this is going now. Now at each time step and for each ground action, if there is an effect which involves updating a state variable, then you include a constraint between the action for time t and the value that the state variable must then have at time t plus 1. So with the previous example, we would have a constraint that says that you can do buy climber 1 gorilla joke shop at time t, provided you also have has gorilla equals climber 1 at time t plus 1. And again, you'll do that for all ground instances of actions, all ground instances of their effects, and all possible times. Now I hope that's clear. I tend to find that it's not something that anyone understands at the first reading. You may have to go away and think about it a little bit, and hopefully it will fall into place without too much trouble. But just keep in mind that all we've done is started with one language for representing plans. It has variables in it. We're turning everything into ground instances. Those ground instances then become either the names of variables or possible values for variables within the CSP. And we've also introduced some extra variables into the CSP to denote what the actions are. Now the final thing we need to do is essentially include frame axioms that say that anything that's not affected by an action will maintain its previous value. So again, for each time step, for each ground action, for each of the state vectors that isn't an effect of that action, we need to put in this case, a ternary constraint, one between three variables, that says you can have the action at time t, provided that when a state variable that isn't an effect of that action has a value v at time t, it also has a value v at time t plus 1. So the action doesn't change it. So that's a general and systematic method for taking a planning problem expressed in the state variable format and transferring it to an equivalent CSP problem. And you can prove, although I'm not going to have time to do it, that there is a solution to the planning problem with at most t steps, if and only if there's a solution to the corresponding CSP. You can also show that if the CSP has a solution, then we can get a plan out of the solution simply by looking at the values assigned to the action variables. So in other words, if you do this starting from t equals 1 and increasing t, then if it's possible to solve this planning problem, you will find a solution, and it's easy to extract the sequence of actions that you need. And that's all I'm going to say on planning, and in the next video I'm going to move on to machine learning.